Welcome back, everyone, to the eCoreAcademy e-learning platform today. My name is AJay back with yet another geometry video for you all. Today's lesson topic is all about circumferences and areas of circles. So this is going to be an introductory lesson to our new unit that's going to be majorly revolved around circles. And of course, we're going to be looking at specifically circumferences and areas of circles, two major properties of circles. And I will get into depth later on with relationships with radius and diameters in my next circle video. But for today, we're going to be focusing on circumferences and areas, and of course, be looking at some of the other major details of circles, such as diameters, radii, and centers. And then, of course, our different measurements, such as radians. But before I jump into today's lesson, please make sure to smash that subscribe button down below. Hit that like button on this video, as well as turning on post notifications by hitting that little bell icon right next to the subscribe button. All three of those things are very greatly appreciated. So today's lesson theme is to take a look at the basic formulas for the area and circumference of a circle. So we're going to be looking at these formulas and, of course, utilizing it and looking at special case scenarios, because as an enrichment program, that's exactly what we do. We key in on these special case problems and situations that you may not cover in school, and that can actually help you, further along the line, maybe in the SAT or some sort of test preparation that you might come across later on. But without further ado, let's jump right into it. So let's look at a basic overview of circles, since we're going to be introducing major parts of circles. Let's look at a basic overview of circles. And then again, do not be worried. I'm trying to put this lesson first by introducing circumference and area, because there's something that you must be or might already be familiar with. And then, of course, let's look later on in a higher specified environment, on a higher focused environment. Will be a hyper-focused environment. We'll be looking specifically at these different parts of circles that are very essential and very important. But we're going to just look at an overview at circles, and then, of course, look at our formulas. So let's look at the parts of a circle. A circle, by the definition of geometry, it's, you might think of it as just, a circular thing that is just existent by all sets of curves. Well, it's much more complex than that, and it can be explained entirely by the law of geometry, by our definition under the laws of geometry. So a circle is basically the set of all points in a plane. A plane is a two-dimensional outlook that are the same distance r from a fixed point called the center. And r is basically representative of a radius, which is the distance from the center to any point on the circle. And of course, you have your diameter, which is a line connecting any 2 points on a circle. So let me just explain this here. A circle is not necessarily created, originally by drawing an arc. That's not how you make an accurate circle. The only way that you can actually make an accurate circle is through, real life constructions or even a digital construction. It requires you to start at a central point. So we're going to start with our center of our circle. So this right here, this dot that I've made here, is going to be the center of the circle that I'm going to create. Now, in real life, if you're going to utilize a construction, what you would do is you'd put your compass point on this edge and then your pencil edge on the other side, and then you just rotate along this central point and then connect it right here at wherever that line overlaps. And of course, that would be your circle, an accurate constructed circle. However, with geometric software or overall a generalization with circles, the 2 values that you really need to know is your center, some sort of central location, as shown here. And you would also need your radius. So the radius is the distance from the center to any point on the circle. So once we figured out our radius, we're going to make our radius that length. And say, for example, it's this length right here. And let's say that that's 4 centimeters right here. What we're going to do is we're going to draw a circle around that. And that would be our circle right here. And on any point on the circle would be the same distance from the center. So they would all be 4 centimeters. And these lines that I'm drawing are all radii of this circle. And then the diameter is basically a line that connects 2 points. And it's always going to be twice the radius. So I'm going to write this here. Diameter equals 2 times radius. And of course, the diameter and radii are always going to be the same length all throughout in any position on the given circle. So a diameter would look like this. connecting any 2 points, it does not have to pass through the center, however. Sorry, no, it does have to pass through a center. So in order to connect any 2 points on this circle, the diameter would be created in order to connect any 2 points on the circle. But the only way that's possible is by connecting them through the center. So your diameter has to go through the center. And as you can see here, this is going to be 8 centimeters right here. I'm going to bold it right here. So this line that I've drawn here connects 2 points on the circle, one right here and one right here. That would have a length, that's a diameter. We'll just label this out. So that's your diameter. This is your radius. And that diameter would have a length of 2 times 4 centimeters because it's twice the length of a radius, and that would equal 8 centimeters. All right, let's move on. So let's look at the circumference of a circle. We'll start with the circumference and then, of course, end with our area. And I'll give you practice problems as we go along. So let's look at the circumference of a circle, but we're not just going to look at the circumference of a circle because we also need to discover what the origins of pi are. And I'm sure many of you have already been acquainted with the word pi or, the symbol pi. But pi has a lot of meaning behind it. You might think, oh, it's just for circles, something that you plug in. It does have a much more complex background to it, and I will be making a video on that probably towards the very end of this course. I want to give a little section for special cases so that you enrichment students can finish off with a bang in this geometry course. But pi is very important, and the reason that I've added it to this slide is because the area and circumference formulas are basically revolved around this very value of pi. So we're going to be looking at the origins of pi, a bit of its history, where it comes from, how it was developed, and what it actually stands for in both of our equations that we're going to be representing and looking at today. So the area and circumference of a circle, like I said, are based off the term called pi. And the symbol pi looks like this. I'm sure many of you have seen it before. It's just like this. Little wave with 2 lines coming out. So that's what pi looks like. And pi was used and heavily uncovered by Archimedes, or it's by Archimedes, who was in ancient Greece, and he was an ancient Greek mathematician, a very popular mathematician. Another person who's also famously known is Pythagoras. So Pythagoras and Archimedes were both around the same time period, and they had a lot of similar beliefs in what they thought of in their perspectives on geometry. And of course, Archimedes had heavily uncovered pi and used it under higher case scenarios, as pi actually stands for and represents the ratio between the radius and the circumcenter. Sorry, that should say circumference. I apologize. That should say circumference. Circumference. The ratio between the radius and circumference of a circle, and that also will relate to the area formula, and I'll be talking about that later. But there is a correlation between the circumference and the area of a circle, and that's why pi is used in both equations, because of that very reason. It makes everything much more, much simpler. So that was Archimedes. One thing that I just want to say is that pi is estimated to be approximately 3.14. That's the most popular approximation. So if you're not given to give a value or any equation that has to relate to a circle, if you're not given basically a scenario in which it says calculate the area of this or the circumference of this or multiply this by pi, if they don't give you the specifics on what to do, I would most likely approximate it to 3.14 and multiply, instead of pi, multiply by 3.14. But the whole pi actually equals like 3.1415926 onwards and onwards and onwards. It's an infinite number. Goes on for an infinite amount. And if you are given another circumstance, you might be asked to give a certain situation in which you would have to represent a fraction that would represent 3.14 or as close to pi as possible. Otherwise, you'd be asked to actually put it in terms of pi. So you could just leave it as, say for example, you're trying to multiply 5 and pi, you could just leave it in terms of pi. If you're asked to do that, you just leave it as 5 pi. That's the most accurate way representation, but if you want an exact value, you would use this. Let's look at circumferences of a circle, and let's actually look at the formula now that we've cleared up what pi actually represents. So the equation for the circumference of a circle is the following. So I'd recommend that you write this down. So circumference, C equals 2 pi r. So it's 2 pi r. And what we're basically doing here is we're taking our pi value and we're multiplying it to the value of 2 times r. So we're taking pi times r, your radius of your circle. We're going to multiply them together, and then we're going to multiply it by 2 to end it off. We can multiply these in any order that we want. That's under the properties of multiplication, in which allows us to do so. And the circumference is basically the distance around a circle, and it's the same as saying the perimeter of a polygon. So it's basically the perimeter of a circle, the distance around that circle. And if we're given this circle here with a 4 centimeter radius, this is our radius, we are asked to discover the circumference. So I'll write this down here, circumference, so that we know our objectives. Circumference. So if we're given that our radius is 4 centimeters, we're going to plug it into our equation. So C, abbreviation for circumference, is equivalent to 2 pi 4. So 2 pi times 4. Now, what I'm going to ask you to do is actually leave this in terms of pi. But if you were asked to, I'll show you what that value will be if you weren't asked to. If you were given the value or approximation, if you're asked to merely multiply by 3.14, the best approximation. So that's C equals 8 pi in this case, because we're just going to multiply across. And that's your answer. That's your circumference. It's 8 times pi. However, if you're asked to simplify that, we know that pi is approximately 3.14. So if we multiply that across, we approximately. So I'm going to change this sign to an approximation sign. That's approximately 25.12, but it is exactly 8 pi because this is unsimplified, but it's the most exact answer that you can get. So this is probably my favorite form of expressing any terms of pi. But when it comes to real life scenarios, you can't be like, what type of radius, circle or fence. Say for example, you're trying to get a circular fence around part of your yard. Say for example, it's a dog pen. Well, what are you going to do if you're given a measurement in 8 pi? You want to be given an approximation so that you can actually utilize that exact measurement to calculate the area of your dog pen. So you would want to be given 25.12 rather than 8 pi and calculate that on your own. So it's much more efficient to approximate. Now let's move on to the area of a circle, and this is part 1, and we're going to be looking at the formula, and then the next slide is the last slide, and we're going to look at special cases with areas of circles. So the formula for the area of a circle is the following. A equals pi r squared. And in this equation, of course, pi represents pi, r represents radius, and the radius is being squared, and then multiplied by pi. So you're squaring your radius and then multiplying it by pi. Due to PEMDAS, the order of operations, you're going to square it first, and then, of course, multiply. The area of a circle is, of course, like any other figure, is the number of square units that it covers. So the total amount of square two-dimensional area that it actually takes up. So we're going to utilize the same diagram as I did before, and now we're going to try and calculate the area. So I'm just going to label this as radius, 4 centimeters, and let's say area here. Now we're going to just merely plug in our known value here. The only value that we need to know is our radius, and that's given here as 4. So A equals pi times 4 squared. So I just put that in parentheses just to emphasize that you're going to square your radius before you multiply it by pi. 4 squared. So that means that A equals 16 pi. And if you were to simplify that, you would get that A equals 50.24. And that's, of course, in centimeters squared. And also try and keep your units always in the answer. I did not in the previous one, so please don't do that. Don't make that mistake that I did previously. Always include your units of measure, because in real life, in a real life application, if you're given that, say for example, you need a dog pen that has a radius of 4 meters, and for some reason you're given, a length or an area of 50.24 blank. That could be centimeters, which wouldn't make sense for a dog pen. It could be, kilometers. You don't know what is actually given. Even though you can approximate, measurements can be quite confusing, especially in geometry. You don't have that, what do you call it? You don't have that luxury of specifying, because you're only given numbers and sometimes not a real life situation. All right, now let's look at special cases for the area of a circle. And that special case is going to be when you circumscribe a circle around a figure. And like I said before, showed you in my previous videos before, I talked about circumscribing triangles. And circumscribing is basically when you take a circle, when you take a figure and you connect all of its points to make a circle that basically touches all of the vertices of that figure and basically connects all of them to make a giant circle. When you're circumscribing, as the number of sides of an inscribed figure increase, so meaning this figure that's inside that circle, as its number of sides increase, the closer that its area is to the area of a circle. And this is basically referring to regular polygons only. Well, specifically regular polygons. It's not always going to be true in other cases. I'm just going to refer to this as regular polygons, as it can apply to irregular polygons as well. But if we're looking at this equation here, as you can see, this is a figure within a circle. It's a dodecagon. So this is a dodecagon. And it's circumscribed by a circle. So it's basically connecting all of its points, a circle that connects all of its points and basically wraps around the dodecagon. Now, if you look at the circle with that's basically wrapping around and circumscribing this dodecagon, you can see that it's actually very close in area. It's larger, obviously. It has to be larger in order to wrap around the dodecagon. However, it's seemingly close in area, and that's because the number of side lengths that you have on a regular polygon, as it increases, it's going to become even closer to the shape of a circle. In any case, whenever you have more and more side lengths, like maybe 15, 20, the shape is going to look less like straight edges and more like a curve. It's going to look more like a circle, as shown here. But if you were to have a triangle instead, say for example here, the least amount of sides, and a circle here, whoops, sorry about that. If we're going to have a circle here, circumscribed, that connects all of its points, as you can see here, it obviously does not look similar to this circle, and it looks much smaller. But this dodecagon looks almost like the circle that is being wrapped around by, and therefore it would have a very, very close area. And this very property can be utilized to, estimate the area of a circle, because if you knew the area of a dodecagon, you can merely approximate that value to be equivalent to the area of that circumscribing circle. All right, everyone, that'll be it for today's video. This has been the eCoreAcademy e-learning platform today. Please make sure to like and subscribe, and of course, turn on post notifications before you leave. Check out our website at www.ecoreacademy.org. That is basically our entire asset there. That's what we offer fully as an online e-learning platform. And there we have full unlocked access to our integrated note sheets, quizzes, and worksheets that go along with each and every single one of our videos, organized into lessons under separate course studies that have all these extra informations and perks such as progress checks, and of course all of these added features. So please go check that out. All you need to do is make an account there for free. We also have all of our contact information up there, but you can always email us at Gmail at eCoreAcademy@gmail.com if you have any questions, if you just want to reach out to us. And finally, visit all of our socials in the description box below. The full link is down there at Facebook, Twitter, and Instagram. See what kind of new content we have there and use our mediums to share all of our videos. Once again, everyone, I hope you guys enjoyed. This has been AJay Raj, and I will see you guys in the next one. Peace.